Hi there. Welcome to the first lecture of EE635, Applied Linear Algebra. My name is Debasattam Pal. I will be your instructor and my co-instructor will be Professor Dwaipayan Mukherjee. In this semester, because we are going fully online, we are going to follow this model that at the beginning of each week, we will upload video lectures for the whole week. The content will be that's going to be covered for that week. So you are supposed to look at these videos, go through them thoroughly, and then during the institute stipulated timetable, uh, the time as per the institute timetable, during those sessions we are going to have live interactive sessions over some uh, video conferencing platform, and there we will discuss these topics, these the material that will be covered during these video lectures. Okay, and these video sessions, these interactive sessions are absolutely compulsory for all of you to attend. The details of that will be shared on Moodle and also on the course webpage. All right. So with this, let us start with the proceedings. I hope my screen is visible to you. Okay, so this is Applied Linear Algebra. We are in lecture 1. What we are going to do is, so as the name suggests, Applied Linear Algebra. So let me just say what this Applied Linear Algebra is all about. But before we start, there are certain things that has to be cleared out, right? So first thing is, as I said, my name is Debasattam Pal. This is my email ID. This is my phone number. Usually, these are very important things to keep in mind, because by this, you will be able to contact me, and if you have any questions or any queries, anything, uh, I will be available here to answer your doubts. But more so now, because of this pandemic situation, because everything is going online, all these lectures are happening online. So this is of utmost importance that you keep these things, um, and like the back of your hand, and so you should always keep these in mind. And whenever required, you feel absolutely free to talk to us. This is my co-instructor. Okay. And this is the course web page. So the course web page is www.ee.iitv.ac.in tilde Debasattam. That's my name. You go there, you'll find a tab called courses. There you will find the course number. Once you go there, you'll be able to see the course web page. At the same time, you will also be able to find the syllabus there. I urge you to look at the syllabus. Right. The other details about the course, like how the grading would be done, how the evaluation process will go, all these details we will discuss during those live interaction sessions. The first of which is going to happen this Thursday. Okay, and then it will go following slot number 12 of the institute timetable, which happens to be Mondays and Thursdays, 5:30 p.m. to 6:55 p.m. Okay, all right. Now let us get on with the proceedings for this course. So in this course in applied linear algebra, what we are going to be interested basically in are the following two questions. Question number one, which we will call problem number one, is solve for x with ax equal to b, where A is a matrix of size m cross n. This here means that this is the set of all real numbers. B is a vector of size m, and x is a vector of size n, but this x is unknown. We are interested in finding this x. Okay, this is a standard system of linear equations. I'm sure you have already seen how to solve these things, but what we'll do here is we'll look at this problem of solving for x in this ax equal to b in much more detail. Okay, we will see what it means. I'm sure you have already seen that, you already know that solving this equation means that you have to look at this matrix A, form this augmented matrix A and then B, yeah, and then do this row operations, the so-called row operations, and then try and find out rank. Then you say that if the rank of A and the rank of A augmented with B, if the rank matches, then there will be infinitely many solutions. I mean, there will be solutions. Possibility is that there will be infinitely many solutions. If the ranks don't match, then there will be no solutions, right? But why is that so? We will also ask questions like, if there are infinitely many solutions, how would the solution set look like, right? And then once we go through these ideas, once we understand these things in full detail, we will ask this question that what are the situations where these ideas that we have learned can be used? That is what takes us to this idea of abstraction. Yeah, so in this course, our aim will be towards um, abstracting out this idea, these key ideas from linear algebra. I mean, key ideas that form the core of linear algebra, which become applicable at various different scenarios. Yeah. The other question that we'd also be interested in would be of this kind. So this, looking at this equation would take us almost till the midsem, and a little, till midsem will mostly be focused on this particular, solving this particular equation. The other equation that we would be interested in solving is this problem number two. Let me use the same font. Problem number two. Here, once again, we have a matrix, but it's a square matrix. Say real. And then we are looking for ax equals lambda x, where lambda is a complex number and x is a complex vector of size n. And both lambda and x are unknown. As you may have already recognized, this is nothing but the so-called eigenvalue eigenvector equation. The questions that we'll ask in this situation would be, the questions that we will ask here would be, how do we find out these eigenvalues, eigenvectors? How many eigenvectors can we find out? Finding out eigenvectors, how do they help us? And then there's this, utmost important question that if I have these eigenvectors, how do they help? How do they help us in solving, some difficult mathematical equations? One point of um, one point that is important to note here is that in this course we are not going to look at the computational aspects as such of these calculations. Those will be covered in the next semester in the companion course called EE636 Matrix Computations. So here we would mostly be interested in the theory of these calculations, right? Okay, so now let us get back to this question of where do we face these equations? Now we are all electrical engineers, we are doing electrical engineering. Then why should we be even learning these mathematical concepts? How does that really help? In order to understand, in order to understand that applicability, let us try and go through some of these applications from, in fact, not just electrical engineering, but from various different fields of engineering. Let us try and see some of these applications, right? We'll see the first application from electrical engineering, namely the use of an electrical circuit. Okay, so suppose we are given with a very simple DC circuit. Yeah, here is resistance, here is another resistance. Let me call this resistance R1, this resistance is R2, there is another resistance R3. This is a simple T network, as you might already have recognized. Right? I want to find out how, and this is a voltage source of value V. I want to find out all the voltage drops and all the currents in all the branches. I'm sure you have seen this before. This is absolutely simple. How do you do this? How do you solve this? Well, let me just jolt your memory, and let me just do it anyway so that you recall how you had done this once. You set up one branch current, you call it I1. You set up another current called I2. So sorry, not branch current, but loop currents. So this is the so-called loop analysis, right? So one loop current I1, the other loop current I2. What do we do? What do we do with this? Well, we know that if we have, okay, so if we apply KVL in this loop, then we get I1 times R1 plus I1 minus I2 times R3, that must be equal to V, right? So this is my equation 1. If I now apply KVL on in this loop, then I get I2 times R2 plus I2 minus I1 into R3 is equal to 0. That's it. That is equation number 2. Rearranging, I can write this these two equations. This is an example of a system of linear equations. Rearranging, I can write them in matrix vector form as R1 plus R3 minus R3 minus R3, R2 plus R3, I1, I2 is equal to V0. Often this is known, these parameter values are known. We need to find out these two. This is unknown. Yeah, this is precisely problem one. You realize that, right? Yeah, this is precisely problem one. This is A, which is known. This is X, which is unknown. This is B, which is also known. The job is to find out this unknown. It's a very simple one. You can just try and see whether this matrix is invertible, take the inverse. Yeah. But what if they're not invertible? So let me try and complicate matters for you, and pose questions like these. For example, if I have instead an AC network, this is L, this is R, this is C, this is the AC voltage source. How do I solve for? Can this be converted into problem number one? Is it possible? Right? If I make it even more complicated, for example, I have L, C, and R. And also there's this voltage source. Suppose this voltage source is just once again a battery. But now, suppose I have a switch here, which is being switched on at t equal to 0. Can this also be converted to problem one? Will we be able to solve this? Just like the way we solved problem number one. It turns out that if we understand the linear algebra behind it, the theory behind it, we will be able to solve all these questions. Okay? Before we go to the next part of this lecture, I want you guys to try out this particular case. R1, R2, R3, R4, R5, R6, R7, and V. This goes to you as a homework. Loop current I1, loop current I2, loop current I3. Write down the equations in this form. A, I1, I2, I3 equals B. Okay? All right then, you solve this problem, then we'll meet the next module. Thank you.